Hello, everybody. Thank you very much for your interest in this talk. My name is Wenbin Yu. I'm currently the Chief Technology Officer of AnaSwift. We are a small company offering solutions for efficient high-fidelity modeling and simulation of composite structures. I'm also a professor in aeronautics and astronautics at Purdue University. Today, I'm going to talk about VABS, which is a unique software modeling composite beams with the efficiency of traditional beam series, but with the accuracy of 3D finite element analysis. The VABS technology was motivated by the need of the Army to provide an engineering solution for composite helicopter rotor blades. Composites was used to make helicopter rotor blades because of its excellent fatigue performance. Usually, a blade could be a few meters long and half a meter wide and a few inches high, and it could be made of hundreds of layers, both the skin and also the spar, because each layer is about 0.1 millimeter thick. And in principle, we can use 3D FEA to provide a high fidelity modeling of this structure. But because the layer is so thin, and to get accurate stress, and each layer could be different, and to get accurate stress prediction, we need to have at least one solid element per layer. Then for a blade, we are talking about the billions of degrees of freedom, then that's become too expensive to be practical if at all possible. And also the blade, if you look at that, not only the motor scale between the length and the width and height, and also the layer thickness, but also, although externally looks simple, but internally could be pretty complex. When you look at the cross-section, here we have skin made of composites, and also we have this bar, we have filling materials. So it's pretty complex, and the lamination theory is not applicable. It's not like typical laminates. And usually what people do is to use smeared property approach to try to simplify a stack or laminate to be a homogeneous material. It's kind of like black aluminum approach. And it's not accurate, although it can, solve the efficiency problem. So another approach which people commonly use is to introduce various assumptions to construct a beam model, such as the Euler-Bernoulli assumptions, Timoshenko assumptions, or other high-order assumptions. But this beam series depends on what type of assumptions you use. It could lose the general purpose and also could lose accuracy. To avoid the difficulties associated with these conventional approaches, we explore the slenderness, which is the smallness of the cross-section with respect to the length, to mathematically decouple the original 3D elasticity problem into a two-dimensional cross-sectional problem, and also one-dimensional beam problem. And the two-dimensional cross-sectional problem is solved by VABS. And the VABS, what VABS does is that take the cross-section, including both geometry and material, to compute a stiffness matrix. This is for Euler-Bernoulli beam model, which could be a fully populated 4x4 stiffness matrix. Then add the input to the beam analysis to carry out the linear and nonlinear statistical analysis, such as, if you want to do a wind turbine simulation, And you could have a multi-body dynamic simulation, and with each blade represented as a beam. For us to use VABS to compute the inertial property, what we do is to try to minimize the kinetic energy loss between the original 3D model and the final 1D beam model. Then the result is a mass matrix. Could be 6x6 mass matrix, depends on where we put the cross-sectional coordinates. And based on the 6x6 mass matrix, we can extract the mass per unit length and also the mass centers and also the mass moment of inertia and also the principal inertial axis. To compute the structure properties, we need to minimize the strain energy loss between the original 3D model and the 1D beam model. And typically in engineering applications, we have 3 common models. One is called the Oler-Bernoulli model, another called Timošenko model, another called VABS model. Here I need to emphasize that although I use the name, but I didn't use the assumptions associated with the traditional beam model, like the Oler-Bernoulli assumption, plane cross-section remain plane and remain normal, and the in-plane remain rigid. We don't take any of these assumptions because we believe this will cause tremendous loss of accuracy for composite beams. And the Oler-Bernoulli beam model is applicable for very long beams and majorly described by 4 fundamental deformation modes, including extension, twist, and tube bendings. And the Timošenko model additionally have 2 transverse shear, which is applicable to not so long beams. So the aspect ratio could be slightly bigger than the Oler-Bernoulli beam model. And the VABS beam model is, in addition to the Oler-Bernoulli beam model, they got an additional deformation mode, is so-called restrained warping. This is particularly useful for thin-walled beams with open sections. And for general composite beams, we could have fully populated stiffness matrix, not only the traditional EI, GJ, EA, this type of engineering constants. And this means that our beam analysis should be adapted to take the fully populated stiffness matrix, because a composite beam could have all kinds of elastic coupling. For example, that for a blade, we can design in such a way it has extension and twist coupling. When you're rotating, you have centrifugal force. Then it also change your angle of attack for the purpose of aerodynamics. VABS can also compute the trapeze effect. What is trapeze effect? Trapeze effect is the fact that when a body or a blade is rotating, you got centrifugal force, then you find that it's harder to twist. The torsional stiffening effects due to the centrifugal force. It can also compute the neutral axis, which is also called tension center or the centroid. But here, because it's a composite beam, it's not a purely geometry concept. It's a combination of the material and geometry. What it means is that when we apply a tensile load at that point, we will not generate bending. And also, it can compute the principal bending axis and shear center. Principal bending axis is basically help us to decouple the 2 bendings, and shear center help us to find the position that where we apply transverse shear force will not generate torque. And VABS can also use to recover the 3D displacements, strains, and stresses over the cross-section. Since VABS is very unique and very different from the traditional beam theory usually take very simplistic assumptions. Then the beam stiffness is just several integrations over the cross-section. But for VABS, actually, we need to solve a 2-dimensional problem. So what VABS does is basically to take the cross-section, which is meshed using finite elements, and contain the information including both geometry and material. Those are the inputs for VABS to calculate the beam properties. This part usually is not available in traditional beam theory because EITJ, they already automatically just calculated based on simple integrations. And these beam properties are needed for any beam analysis to predict the global behavior, including both dynamic and static behavior. And the VABS can also take the global beam behavior, for example, shear force distribution, bending moment distribution through the span to recover the three-dimensional displacements and strains and stresses over the cross-section. And as far as the use of the VABS, it can be used independently for the structure design of the beam sections, including geometry, for example, where do I put my web, how thick my skin should be, and the material, how do I lay up my material. And for example, we could have a case that I want to maximize my torsional stiffness, but I want to maintain my center of gravity fixed. And then you can use VABS to do that, because both the objective and the constraint are the outputs from VABS. And VABS can also be used along with the finite element beam model to power the conventional beam elements with the fidelity of 3D detailed FEA for not only the prediction and also geometry representation with negligible additional computing time compared to the traditional beam theory. And we do have to emphasize that the beam elements should be modified to accept fully populated stiffness measures. Quite a few commercial codes has already made that change to take the inputs from from VABS. And VABS as a software, but it comes from over almost over 3 decades of vigorous research. And it's a unique technology, has been continuously funded by US Army since 1988. It's 32 years today. And it provides a satisfactory solution for composite helicopter rotor blades. We are currently under support from US Army ERDC to use VABS to build an efficient high-fidelity framework for structure design and optimization of composite lifting bodies. And we are also under support of the US Air Force to develop an integrated computational blades engineering for rapid insertion into eVTOL and ORB vehicles. It now becomes a tool of choice for helicopter and wind turbine industry. And not only VABS can be applied to predict and model helicopter rotor blades and wind turbine blades, and it can also be used to deal with propellers and the eVTOL blades, we just mentioned, and UVAs, and the landing gears, and high aspect ratio wings, and golf clubs, and the tubes, rods, and columns, and poles, and other structures modeled as beams. So these are the typical applications that our customers tried and used the VABS for. And basically that as long as it's slender, which means we have a cross-section much smaller than the length, the span of the beam, have the third dimension, then VABS can help you if you want to model it as a beam for quick design analysis. VABS has been extensively validated in the literature and also in industry. In this paper that's been 20 years ago, we provide a critical assessment of VABS against other tools for calculating composite wind turbine blade properties. And we found out that VABS has been consistently outperforming the other tools for the turbine blades, particularly for the couplings, the elastic couplings, and the other tools usually has difficulty to deal with that, also torsional stiffness and shear centers. But VABS has been consistently excellent in terms of prediction when we compare with more high fidelity 3D finite element analysis. And we also validate VABS against 3D FEA. This is an example of a realistic rotor blade made of different materials and composites, and has a 100 degrees C temperature increase. We are asked to compute the thermal stress. And typically, people, with the VABS, if you want a good thermal stress results, people rely on 3D FEA with solid elements. For this model, for decent results, we require almost 5 million degrees of freedom. But if you use VABS, we only need to carry out the cross-sectional analysis. Then we can generate all the stress results. Those are the contour plots of the stress distribution to quantitatively to compare the stress distribution. We take a load path through the cross-section and to plot the stress distribution along the load path and compare with the 3D FEA. We find out that we can accurately reproduce 3D FEA results. We also find out that we not only have this axial normal stress, longitudinal stress, we also have other stress components, the normal stresses, transverse normal stresses, and also transverse shear stresses. Usually a beam theory can only give you approximately correct longitudinal stress and also the longitudinal shear stress in two directions. And we have the capability to compute the complete 3D stress and strain fields and still use simple engineering beam models like Ola-Bernoulli model and Tim-Single model and without the associated assumptions. And we can achieve this 3D FEA accuracy, enable us to capture ply level details in seconds. And usually for a realistic rotor blade or other composite beams, it's impossible to use 3D FEA to get the ply level details. And in a realistic environment, usually how you do it, you will find out that VABS can be used as a component of your entire workflow. For example, to design the wind turbine blades. Usually how people do is that they cut multiple sections, dozens or hundreds of sections along the length. Then for each cross-section, we need to use VABS to carry out the cross-sectional analysis to get the corresponding cross-sectional properties. These cross-sectional properties will be put into the one-dimensional beam finite element analysis to carry out the static, dynamic, linear, or nonlinear analysis. After we finish the beam analysis, we will get the global behavior in terms of force and moments and curvature and strains and deflections. Then we can do recovery of the stress over the cross-section. Then we can identify where the stress concentrations happens, where are the hot spots, where we need to put more material. And this approach particularly valuable for the preliminary design, the phase 1 design, and at a certain stage, people may want more, use for 3D FEA if it's possible to validate the final design. But 3D FEA is too expensive and cannot be used for treat studies. And we recently integrated VABS with Altair products, particularly HyperMesh and OptiStruct and HyperView. We use HyperMesh as the pre-processing and the VABS and OptiStruct, VABS as a solver for OptiStruct and HyperView to visualize the results. Regarding the details, for example, that we could have a channel section, and what we do is that we create this model in HyperMesh, then we do section cut in HyperMesh, And since the cross-section could change along the length, we could have multiple cross-section cards, then split to two types of files models. One is the one-dimensional beam model, then contain multiple two-dimensional cross-sectional models. Then next, we invoke the VABS to compute the cross-sectional properties for each cross-section as input to OptiStruct beam elements to do the finite element analysis. And at the end, we output stress and strain and one-dimensional results for visualizations. And comparing to the previous OptiStruct, because of the addition or integration of VABS, we have several enhancements. First, that the curved and twisted composite beams now can be analyzed within one single run of OptiStruct. Second is that VABS can be invoked internally. And there are three types of enhancements. First, you can directly use OptiStruct to load VABS to do the calculation of the cross-sectional properties. Second, you can identify particular beam elements within an OptiStruct 1D beam finite element model to specify which properties will be computed by VABS. And third is that we updated that the beam elements for OptiStruct now can account for fully coupled stiffness matrix. So as a conclusion, that the VABS is a code, is a software within APA right now, provides an efficient high fidelity alternative of 3D FEA for slender composite structures. It can compute the best complete set of beam properties, which are needed for static or dynamic analysis of beam elements. And the second, it can compute complete set of accurate 3D fields, particular stress and strains, and is also highly optimized for efficiency. It can capture ply-level details of real blades in seconds, and it has been extensively validated in helicopter and wind industry. And we have directly integrated the software into the Altair products. It's also an essential piece for model scale simulation of slender composite structures, which we can link the material properties to the structure analysis directly. So this is the end of my presentation. Please let me know your questions. Thank you.